Thank you. No, it's very great. It's a great honor to speak at Noga's birthday conference. Unlike many of the speakers, I've only known Noga for a fairly short time, I think 10 years or so. Mostly in conference, in committee work, actually, is where we mostly meet. Not have very many interesting stories, except... huh? Oh? Is it not on?
Move the mic a little.
Oh.
Or top.
Okay. Okay. Yeah, so I don't have many stories to tell, unfortunately. I will say, though, I always encounter Noga's work whenever I do my own. There's been at least 3 occasions I know of where my co-authors and I came up with some really clever arguments to get around some obstacle in our research, and we were very proud of it. It's a nicely original, cute argument, and we've later found that Noga had done it, 10 years earlier. But anyway, and every time he's in the audience when I give a talk, he guesses the punchline about halfway through. So I hope you don't spoil it this time. Okay. Okay, so I'll be talking about the discrepancy problem of Erdos. So let me start with some definitions. So whenever you have a sequence of numbers, which I'll call f of 1, f of 2, f of 3, and so forth, real numbers, complex numbers, actually more generally, as it turns out, it's more natural to think of them in a Hilbert space. We can find the discrepancy of the sequence. What you do is that you take partial sums of the sequence along any homogeneous arithmetic progression. So a homogeneous arithmetic progression is something from d, 2d, 3d, up to nd for some natural numbers n and d. So you sum your sequence along your homogeneous progressions, and you find the biggest discrepancy among all these sums. You take the magnitude of this number or vector, and you take a sup over all n and d, and this we will call the discrepancy of your sequence. And so that's some number, could be infinite. In fact, the Erdos discrepancy problem, which was formulated by Erdos in the 1930s, is the following question. So suppose you have a sequence which consists of numbers which are only +1 and -1. So if you have a sign pattern, an infinite pattern of +1s and -1s, is it necessarily the case that the discrepancy is infinite? So in other words, can you find homogeneous arithmetic progressions on which the sequence is arbitrarily unbalanced? That if you sum the sequence on that homogeneous progression, that the magnitude gets as big as you please. Okay? So this is the discrepancy problem. So it's difficult because of this homogeneous requirement that you're only allowed to sum over progressions that are basically sort of start at 0 in some sense. If you consider all progressions, the question is easier. So if you take the sup over all progressions, a plus d, a plus 2d, and so forth, then the problem is easy, at least by modern standards. So for example, we have this classical theorem of van der Waarden that whenever you color natural numbers, you can find arbitrarily long monochromatic arithmetic progressions. So in particular, if you have a sequence of +1s and -1s, you can think of these as 2 colors, then you can find arbitrarily long progressions on which f is either all +1 or all -1, so the discrepancy is going to be k, at least for any k, so of course you have unbounded discrepancy in that case. Now, the bounds in van der Waarden's theorem are famously bad, at least for our current level of understanding. They've gotten better, but they're still bad. So there's a more quantitative result, famous result of Roth, not his most famous result, but still a pretty good one, more quantitatively, if you take a finite sequence of signs, f1 to fn, then you can find an arithmetic progression, not homogeneous, but a non-homogeneous arithmetic progression in there for which the discrepancy is fairly big. The discrepancy on that progression you can make about as big as n to the 1/4. So that's a nice result of Roth. That turns out to be sharp. I think that's the result of Matuszek and Spencer. Okay, sorry. Okay, okay. Okay, but these results, they all depend very much on the translation invariance. That if you shift an arithmetic progression by a constant, you get another arithmetic progression, and that is certainly not the case for homogeneous progression. So these techniques don't seem to do much for the homogeneous problem, for Erdős' problem. Okay, and in fact, if you restrict to homogeneous, so the Roth discrepancy theorem says that discrepancy can be quite large, and it has to be quite large, it has to be at least as large as n for 1/4. Once you make it homogeneous, it's actually can be a lot smaller. I think maybe that's not this next slide. No, it'll be a little bit later. Okay, so so this problem has been worked on and off for many years. So most recently, in around 2010, Tim Gowers, so this was already mentioned by Gil in his talk, that 2010, Gowers started one of his polymath projects to attack this discrepancy problem, hopefully to solve it. So they didn't quite solve it, but they made a number of important reductions and observations which became useful later. And actually, there's some good reason why they couldn't solve it at the time, which I'll get back to. But but now we can. Okay, so that was Tim Gowers' project. All right, so some other background about the problem. So I stated the question in sort of an inventory setting. So you have an infinite sequence of plus ones and minus ones, then it has unbounded discrepancy. There's an equivalent finite version. There's a standard compactness argument that lets you convert it to a finite problem. An equivalent form, which is this finite form, is that given any constant c, there must exist a finite length n, such that if you take any finite sign pattern of n plus ones and minus ones, any finite sign pattern of this length must have a discrepancy at least c. Okay, and so n depends on c. So if c is say 10, there must be some n such that for all sequences of length n, the discrepancy should be at least 10. Okay, so this is a finite version, and so being so finite, you can actually start, numerically computing this. So for each c, what you can actually start working out what n should be. And it turns out that n actually grows fairly quickly in c. So for example, well, first of all, if c is 1, that's a fairly easy case. Okay, so if c is 1, how long does your sequence have to be before your discrepancy is at least c? Well, that's 1. Okay, first, even one number 1, that gives you a discrepancy of 1. 2 takes 5 minutes to do. It's actually a fun 5 minutes. Okay, so if you can check that if you have a sequence of 12 plus ones and minus ones, then somewhat inside this sequence of 12 signs, there must be a homogeneous arithmetic progression whose discrepancy is at least 2. And this you prove basically by solving a little Sudoku puzzle. That if this wasn't the case, then every homogeneous progression has to have discrepancy -1, 0, or 1. So for example, you can't have 3 plus 1s in a row and things like that. And you just start filling the signs. The first thing at 1, it's either plus or minus 1 without loss of generality. 1 is a plus, and you start filling in the signs, and you fill out everything, and you will get a contradiction at 12, and at 11 you don't. So that's c equals 2. And c equals 3, this already is much less trivial. So about a year or two ago, it was actually worked out what the minimal n was. It turns out to be 1161. So there is a sequence of signs of length 1160 where the discrepancy is always 3 or less. Is 2 or less. But for any sequence of the form 1161, there has to be somewhere in there a homogeneous progression of discrepancy at least 3. So they didn't just check all 2 to the 1161 cases there. Okay, so they basically did, so rather than a Sudoku calculation, they had to do a big 3-stat calculation. And so they used a state-of-the-art customized stat solver, and they actually did it, and they provided a verification file, which it turns out to be 13 gigabytes, which is roughly the size of Wikipedia. So this actually, there were some media articles about this. This was claimed to be the world's largest proof. Okay, so the polymath project had also done some numerics. So they got pretty close. They found a sequence of length 1124 which had discrepancy 2, but they didn't do this. They couldn't do the stat verification. Okay, c equals 4 is not known exactly what the minimal n is, but we know it's at least 13,000. Okay, so there's a sequence like that. Okay, so it grows fairly quickly. The n as a function of c. All right. here is a sequence of 11 signs of discrepancy 1, which, all right. Here's a sequence of signs of 1160 signs of discrepancy 2, and I'm not going to show you the 13,000. And yeah, so you can check that. Okay, maybe Noga can. Okay. All right. So, okay, that's for small c. What about for larger c? Well, there's a nice example that gives you some indication of how n should go in C. So this is a nice example of Borwein, Choi, and Koons. So it's the following. Define the following sequence. F of n is either +1 or -1, depending on what the last non-zero digit is, or maybe the first non-zero digit is in the base 3 expansion. So you expand out n base 3. You look at the lowest, at the rightmost digit, which is not 0. So it's either 1 or 2. And if it's 1, you set f of n to be +1. And if it's 2, you set it to be -1. So it's so that's some sequence. And you can check that if you sum, say, the first n terms of the sequence, this turns out to actually equal the number of ones in the base 3 expansion of n. And actually, if, this sequence is multiplicative, that f of nm is the same as f of n of f of m, because basically it's a modification, a variant of the Dirichlet character, or non-principal Dirichlet character of conductor 3. So there's a brief calculation that if you set n to be just the sum of the first k powers of 3, 1, 1, 1, 1, 1 in ternary, then the discrepancy of the sequence can be computed exactly, turns out to be exactly k. So you can find sequences of size about 3 to the k whose discrepancy is about k. So the discrepancy can grow about logarithmically, or to put it in terms of c and n, for any c, the least n that you can use has to grow at least exponentially in c, which is kind of consistent with the numerics that you saw. Okay. All right. In fact, this example is a fairly simple example. It's basically the best known up to constants of how slow the discrepancy can grow. So this is about the slowest discrepancy sequence of length n that we actually know about. It's much better than the random sequence, by the way. If you just pick n random signs from 1 to n, the discrepancy is roughly about square root n. So that's pretty large. So the random sequences are not the enemy here. The enemy is very structured sequences, like very periodic sequences with lots of cancellation, lots of very structured cancellation in them, not random cancellation. That's not the problem. Yeah, these are very sub-random sequences in some sense, low discrepancy sequences. Okay, so yeah, so the Borwein-Choi-Koons example is completely multiplicative, and that turns out to be basically the most important case. So an important subclass of sequences for this problem are what's called the completely multiplicative sequences, the sequences such that f of nm is equal to f of n, f of m for every n and m. So this Borwein-Choi-Koons sequence is one example. Another important example from number theory, which I'm going to use as a running example later, is what's called the Liouville function. The Liouville function, lambda of n, is defined to be -1 to the number of prime factors of n, counting multiplicity. So lambda of 2 is -1, lambda of 6 is +1, and so forth. So that's a completely multiplicative function. The reason why completely multiplicative functions are relevant is that they're more likely to have low discrepancy because for a general sequence, you have to test all homogeneous progressions, and there's a lot of them, and there's a good chance that one of them at least is going to have a large sum. But for a completely multiplicative sequence, you have to test fewer, because if you're summing a completely multiplicative function on a homogeneous, maybe I'll write it down. If you have a completely multiplicative function and you're summing it on a homogeneous progression, then it can factor into a sign times f of 1 plus f of 2. Okay, so this sum has the same magnitude as this sum. So if you want to get a lower bound on the discrepancy of these guys, you just need to get a lower bound on the partial sums of f. Or conversely, if you want to find a low discrepancy sequence which is completely multiplicative, you just need the partial sums to be small. Okay, so there's a special case of the discrepancy problem which looks simpler. So if you restrict attention to just completely multiplicative functions, is it the case that the partial sums of these guys are unbounded? Are the partial sums of any plus 1 minus 1 sequence unbounded? That's a consequence of the general positive answer to the Erdos discrepancy problem. So Erdos already posed this back in like 1950 as an important special case. And this was, in fact, even this special case was not solved until last year. So, for example, as a special case of the special case, the partial sum of the Lugol function should be unbounded, which is true, but I don't know of any really elementary proof of that fact. It's fairly easy if you know about the zeta function, and in particular, the zeta function has at least 1 0 in the critical strip, which is true. That's already enough to get it for lambda, but that's a sort of a specific number theoretic fact which is special to lambda, and it doesn't seem to give any insight what to do in general. Okay. All right. Yeah, so the next comment I want to say is that there's another special type of completely multiplicative function which is relevant, which are the Dirichlet characters. Dirichlet characters are multiplicative functions which are periodic of some period. So a good example is a function which is plus 1 when you are n 1 mod 3, minus 1 when you're 2 mod 3, and 0 when you are 0 mod 3. That's a Dirichlet character. So Dirichlet characters, as long as they're non-principal, if they're not just 1 everywhere, 1 and 0, if they actually have a sign, then they're periodic and they have mean 0, which means they have bounded partial sums. So Dirichlet characters do have bounded partial sums and are completely multiplicative. They are not a counterexample to the discrepancy problem. They are almost a counterexample. They're not a counterexample because they do take 0 sometimes. It's important for the discrepancy problem that you only allow to take plus 1 and minus 1. If you allow to take 0, then of course you can have 0 discrepancy. You just have to take the 0 or 0 sequence. But these are sort of almost counterexamples of these Dirichlet characters. They have bounded sums. They're completely multiplicative. They just happen to be 0 a small portion of the time. For example, this character I just said is 0 1/3 of the time. You can try to fix it. You can try to fix. You can try to modify your Dirichlet character so it's not 0 at say multiple 3. And this is where this Borwein-Choi-Kuhn's example comes from. You can think of that as the most natural modification of the Dirichlet example to make it non-zero. But then the discrepancy grows a little bit. But what this suggests is that the enemy is not random sequences or anything. The enemy is really the worst sequences, the sequences with the lowest discrepancy, should be sequences that are sort of almost Dirichlet characters in some sense. There's actually a specific term for this nowadays in number theory. There's Granville and Sandaraj introduced the concept of pretentious number theory, what they call it. They define a notion of what it means for two multiplicative functions, one of them to pretend to be like another, which is sort of, there's a metric in which they can be close. And yeah, basically functions which pretend to be like Dirichlet characters in a certain technical sense are the enemy. Okay, so that's for the background. Okay, and so what I want to talk about is the solution to this problem. So last year I managed to solve the problem. That in fact the problem has a positive answer. Any sequence of plus ones and minus ones has infinite sequence of plus ones and minus ones has unbounded discrepancy. In fact, I put a slightly stronger statement. So it doesn't have to be plus ones and minus ones. Any sequence which takes values, say a unit complex in the unit circle of complex numbers, or more generally still in the unit sphere of any Hilbert space, will have unbounded discrepancy. This actually turns out to be the more natural formulation of the problem. Okay, so it's less combinatorial, but somehow it turns out to be more natural. And so a corollary of that is that any complete multiplicative function which takes values in the unit circle now will have unbounded partial sums. Okay. All right. Actually, so this is a corollary of the main theorem, but actually there's a stronger corollary which is more relevant. Not only does any specific multiplicative function have unbounded sums, but in some sense, any random multiplicative function also has unbounded sums in the following sense. This is a slightly technical slide, I apologize. But there is a stronger version of that corollary. Suppose you take a multiplicative function which is random. So so there's a specific definition here. So there's some probability space, and for every point in your sample space, there's a different multiplicative function attached to that point in the sample space. And so you have some sort of random multiplicative function. So for every prime p, you choose some random, say plus minus 1 or something, okay, and then this just generates some random function. If you take any random multiplicative function, the random partial sums are also unbounded in expectation. So this doesn't follow because, I mean, if each individual random sum, if each individual multiplicative function has unbounded partial sums, it could be that when you average, it all cancels out. But even with averaging, these guys should still be unbounded. There's a random version of a corollary which is also true, and for this you need the Hilbert space version. The way you prove this is that if you have a random multiplicative function, its value at any given number n is a random variable on the unit circle, but you can think of that as a function in L2 of your sample space, and that's the Hilbert space. So so there's a proof which maybe you should ignore, but if you just apply the Hilbert space version of the discrepancy problem to these vectors in L2, and you just write it out, you will get this probabilistic version of this corollary. Now, the reason why I emphasize this corollary so much is because of the surprising fact that this looks like a special case of the full problem, but it's actually equivalent. So one of the things that actually the Polymath 5 project did actually work out was the following nice equivalence, that the Hilbert space version of the discrepancy problem not only implies the unbounded average discrepancy of random multiplicative functions, but conversely, if you can prove unbounded discrepancy of completely multiplicative functions, you get back the Erdos discrepancy conjecture for all sequences in taking values in Hilbert space, which sounds surprising because not every function is multiplicative, right? Most sequences are not multiplicative at all, but we have the wonderful tool of Fourier analysis. And so basically what you do is that if you take any sequence taking values in, say, the unit sphere of the Hilbert space, roughly speaking, you can write it as a superposition of multiplicative functions, which are like characters on the natural numbers. Now, there's some caveats here because the natural numbers are not actually a group under multiplication, they're a semi-group, and they're not compact, and so there's always truncation and massaging that you have to do to actually make this argument rigorous. But ignoring that, roughly speaking, you can write any arbitrary sequence as a combination of multiplicative sequences, and you just fiddle around with Poincaré theorem, and you can write the discrepancy of your original, you can relate the discrepancy of your original sequence in terms of some sort of average discrepancy of the partial sums of these completely multiplicative functions, and if you just work it all out, these random multiplicative functions naturally emerge. And so it's basically Poincaré's theorem. So what this tells you, roughly speaking, so it's a technical reduction, but roughly speaking, what it tells you is that multiplicative functions are the worst case. That if you can solve the discrepancy problem for multiplicative functions, I mean, technically you have to talk about random multiplicative functions, but roughly speaking, multiplicative functions are the key test case. If you can do that, you should be able to do everything. So just for sake of exposition, so let's just focus on the special case. So really the key is to solve this problem. You really want to prove that every multiplicative function has unbounded partial sums, taking values in, say, the unit circle of the complex numbers. Okay, so this begins to move away from combinatorics and begins to look a lot more like number theory. Okay, number theory really is obsessed with multiplicative functions. And so actually this was one of the reasons why the Polymath project didn't actually solve the problem. So they identified this reduction, and at the time the conventional wisdom was that understanding partial sums of multiplicative functions was just insanely difficult, as hard the twin prime conjecture and so forth. And so they decided let's not try this approach. Let's try some other approaches, which were quite interesting, but also unfortunately stalled out later. the point was actually in 2015 there was a breakthrough in number theory which allowed one to move forward on this sort of number theoretic approach to the problem, which was not available at the time of the polymath project. Okay, so so we can reduce to maybe so I actually worked on the polymath project back in 2010, and then I'd forgotten about it by 2015. And I was working on something else in number theory, actually. I was working with some co-authors of mine, Kaiser Matamaki and Maxim Radziwill, on upper bounding sums of multiplicative functions, basically. And I posted it on my blog. And there was a blog comment on my blog saying that, some of the calculations you're doing sound similar to the calculations that showed up in Polymath 5. There was some new, I had referred to some of the things I was doing as sort of playing the Sudoku puzzle, and a lot of these numerics trying to find low discrepancy sequences, they also have this sort of Sudoku flavor to them. And so the person on the blog commented, asked, do you think there's any way that you can apply these methods to solve the discrepancy problem? And I replied to my blog, you can still see it. No, I don't think so, because the results I had were all about upper bounds of sums of multiplicative functions, and this question is about lower bounds of sums of multiplicative functions. They're completely unrelated. And so, there shouldn't be a connection. And so I had this sort of naive response. And then someone else asked a very similar question, and I thought about it a bit harder, and actually I realized there actually was a connection. So I was very grateful to my blog commenters, actually, for pointing me towards this. There is a way, this is a question about lower bounding partial sums, but there's a way to use upper bounds on partial sums to get lower bounds on partial sums. And so this is something that I had missed. So to motivate this, let me talk about a toy problem. So here's a classical fact in number theory, which I'm going to give a proof of. So suppose you take an irrational number, root 2 or something, alpha. And then you look at this function, the function that takes any natural number n to e to the 2 pi I n squared alpha, so a quadratic phase. So that's a fairly random-looking phase. The basic fact that we're going to prove here is that this has unbounded partial sums. You take the partial sums, these are called Gauss sums, incomplete Gauss sums. Okay, so these incomplete Gauss sums, they're unbounded in n, which is not so surprising because if you add n random numbers, they should behave like root n, which, so it should be unbounded. This is not a new fact, but I'm going to give a short proof of this. Now, this is not directly relevant to the problem because this is not a multiplicative function, but this will illustrate the idea that you can use upper bounds to get lower bounds. Okay? All right, so how do you prove unbounded partial sums? Okay, so you read Alon Spencer, you use the probabilistic method, of course. Okay, so let's see how you prove this. Okay, so you pick a large number x, a really large number x, and some moderately large number h, let's say log x or something. And what we're going to do is that we're going to pick a random number between 1 and x. So you just pick a random natural number between 1 and x. You look at a little window of this sequence. So you look at a short interval of this sequence, f of n plus 1, f of n plus 2, f of n plus k, f of n plus h. So if n is random, you can think of these h numbers as h random variables. And all these random variables, because of the irrationality of alpha, they all have unit magnitude. They all have mean about 0, because these numbers are sort of equidistributed running in a circle. These are h numbers of mean 0. Their variance are basically 1. And you can check also, not only do they variance 1, but their covariance is almost 0. That if you compute the inner product between any two of these random variables, you subtract two quadratics, you get some linear phase times some irrational number. This is still equidistributed. So you can check that these h random variables, they have mean 0, variance 1, and covariance is basically 0. So when you sum them, the total variance of this is about h. And so that means that these sums have to be at least the size of root h some of the time. And that's already enough to show the partial sums are unbounded. Okay. So basically what you need is an upper bound on the covariances. And if you can bound get upper bounds on covariances, you can get lower bounds on these partial sums. Okay, so there's a connection between lower bounds and upper bounds, but it's very classical. This is related to the van der Kolper trick in equidistribution theory. Okay, so if you actually work out all the details in general, if you want to show that a function f is unbounded partial sums, you just need to prove some non-trivial bound on correlations. You want to bound, you look at the correlation between f of n and fn plus h, these covariances basically. If you can, so this type of sum is bounded by x trivially. If you can get any little o gain over the trivial bound, that's enough to get unbounded partial sums, as it turns out. Actually, for technical reasons, we don't focus on these averages. We focus on a smooth version, what I call a logarithmically averaged version of these averages, where you divide by n. Now the trivial bound is like log x, and you just want a little gain over log x. But okay, that's a it's an important technical detail, but this is the type of sum that you would like to do. If you can bound these sums, then you're done. Now, so the polymath project got about this far, and then at this point they got scared off because in the special case of the Liouville function, this sort of bound is not known. It's open. So even for this model case of the Liouville function, for which we do know by other means that the partial sums are unbounded, these correlations, they are conjectured to be small. Okay, there's conjectured to be no correlation between lambda of n plus h. So this bound is conjectured to be the truth, but it's still not known. And the belief was that this is about as hard as the twin prime conjecture. It looks a little bit like asking for a prime for n and plus h to go through prime. It is related, but it was believed that this was hard, and so this is what caused the polymath project to move into other areas. But it turns out, so this is really the key to the whole business, is that well, this is still out of reach for now. But if you average it, if you put this weight n, it turns out that this average version of this conjecture, this is called the Charler conjecture. Actually, it's a special case of the Charler conjecture. If you can prove this bound, some non-trivial cancellation on this sum, that's enough, at least for the Liouville function, to prove the Liouville function is unbounded. And this is what actually I managed to do. I managed to show that this type of sum has some cancellation. And there's a more general statement where you replace lambda by more general multiplicative functions, and this shows that other multiplicative functions are unbounded as well. I think maybe just for the interest of time, we'll just focus on just the Liouville function, which already sort of captures most of the ideas. So so the main new input is this new number theoretic estimate that you get some cancellation between the Liouville function at n and the Liouville function plus h. Okay. And as I said, you can do something similar for other functions, but let me just skip all that. So actually, just for simplicity, let me take h equals 1. So even just adjacent values of the Liouville function to get some cancellation between this sign and this sign, let's just focus on that case for simplicity. Okay. Yeah, so, we know some stuff about the Liouville function. But a lot of the facts that we know about Liouville function, they're sort of linear. You can bound various things that sort of involve one lambda. And so what's hard about this sum is that it involves two copies of lambda. But we have a lot of things that involve one copy of lambda. So for example, we have the prime number theorem. Prime number theorem tells you one equivalent form is that the partial sums of one copy of lambda have some cancellation in them. That at least one copy of lambda, you have some cancellation. And there's various variants of this. So I just wanted to, for example, you can twist lambda by some linear phase, and you also get some cancellation. You can insert all kinds of other things in here nowadays, but you can at least get a linear phase. Now, more recently, there have been local versions of the prime number theorem in some sense. So rather than sum lambda along the entire interval from 1 to h, you can ask for something harder to do, which is you sum over short intervals between n and n plus h, and you'll ask for cancellation on short intervals. Maybe it's to make your life a bit easier, not on every short interval, but maybe you average over all short intervals. You ask, can you get cancellation in, say, most short intervals? And so there are these more technical-looking variants of the prime number theorem where you average over short sums and you still ask for cancellation at short scales. And this is the breakthrough that happened in 2015. That Matamaki and Radziwill were able to also get this very local version of the prime number theorem, where h can be really quite small. In fact, the amazing thing was that they were able to get a good bound even for h much, much smaller than x, as long as h still went to infinity, but as a function of x, but arbitrarily slowly. So log x, you still got a bound, which is really quite amazing. And essential, actually, for what I need, that h is so slow. Okay, so they proved a bound like this, and then later I worked with them. We found various improvements. Yeah, so, for example, we were able to also stick in a linear phase and things like that. So we were able to get certain, so you can control lambda on short intervals, which is great, but these are still linear estimates. They only involve one copy of lambda. And the type of estimate we need has 2 copies of lambda. And it was known, so there's this famous problem in number theory called the parity problem, which basically, roughly speaking, says that if you only have linear information on a sequence like lambda, then there's certain bilinear estimates that involving 2 copies of lambda that you can't deduce just from linear information. There is a, for example, if you want to prove something like this involving 2 copies of lambda, you can't prove it just, no matter how many estimates on 1 copy of lambda, even the Riemann hypothesis is not enough. One way to think about this, and I guess it's appropriate given that this is a conference for Noga, is that the reason for this is that this sum has no expansion in it. You can think of this sum as a sum over a graph. So there's a very stupid graph here where you take all the natural numbers as your vertices and you connect n plus 1 as your edges. So it's an infinite path, if you like. And what you're doing here is you're basically computing some bilinear, so every graph has an adjacency matrix, comes from a bilinear form, and you're basically just computing this bilinear form. There's a weight, but it doesn't ignore the weight. You compute the bilinear form against this sign pattern lambda. Now, if this graph was an expander, then you have this mixing lemma, and you'd be able to control this sum quite well as long as you understood the mean of lambda, which we do by the prime number theorem. So if this graph is an expander, then we'd be in great shape. Now, of course, if the graph that connects n to n plus 1 is very much not an expander. And so you can construct all kinds of lambdas for which there is no cancellation in the sum, but which lambda looks very random. Any linear test for lambda is indistinguishable from random noise, but for which this sum is big. Basically, you can break up the natural numbers into pairs, and each pair you put plus 1 and minus 1 randomly in each pair. And that would have a big correlation here, but all linear correlations would be small. Yeah, so the problem is that we are summing over a graph with no good expansion properties. Okay, but lambda is not a complete arbitrary sequence. It has an additional property. It is multiplicative. And so you can use that. Okay, so lambda is multiplicative of primes. So for any prime p, lambda of p times n is minus lambda of n. Remember, lambda of n is just minus 1 to the number of prime factors of n. So if you make one more prime, you flip the sign. So you can play with that. If you use this multiplicativity for some small prime p, some p much less than x, think of p like log x or something. If this sum is big, okay, so we're trying to prove the sum is small. If the sum is big, then you can dilate, you multiply n by p and you play around with it. If this sum is big, then this related sum is also big. So instead of shifting n by n plus 1, you look at n and n plus p, where n is also constrained to be divisible by p. Okay, whenever you have this, you can divide n by p, and this sort of sum, this sort of expression is actually basically this type of expression in disguise. You do change your variables. And here, this technical weight 1 over n is crucial, actually, in order for us to change the variables without changing this x very much. Otherwise, you have to replace x by x over p or something. But okay, there's a technical, this weight gives you sort of a dilation invariance, which is very important. But if this sum is big, then you can dilate by p using this multiplicativity. And so this sum is big as well. Okay, so what? So this is like a graph. This is like another graph, which is where you connect n to n plus p whenever n is a multiple of p. Now, that's also not an expander. Yeah, Noga's already guessed the punchline. Okay, but then what you can do is you can average all these together. Okay, and so if this is large, then also another more complicated expression is large, where you average over all p in a certain range, the p comparable to some h. So this is a sum over a slightly more interesting graph, where for all p's in a certain range, you connect n to n plus p if P is divisible by N. So if you like, for every prime there is an arithmetic progression mod P, and you're connecting them by chain, by a path, and so you're laying down all these paths together. And so now you have a graph which is more interesting. It's not just one path, it's a whole bunch of paths. Now, so this graph I think I call GH on the next slide. Yeah, so this is a connected sum with some graph GH. Now, if this graph was an expander, now it's okay. Technically, it's not an expander even because it only connects elements to nearby elements, and so globally it is not an expander. You have to define expander loosely. What I mean, roughly speaking, is take short segments of this graph. This short segment should look like an expander on the average. If this graph was an expander, then we'd be in great shape. If it had some local expansion properties, you could control this expression by local sums of the Luba function, and that's exactly what Matamaki and Radziwill were able to do. And so if this graph, this funny graph that I just talked about was an expander, we'd be done, actually. Now, unfortunately, so I've tried. I've not yet been able to prove this graph is an expander. I can prove some diameter. So with Matamaki and Radziwill, we prove some diameter bounds. We prove things that are consistent with expansion, but we haven't actually proved expansion. But there was a trick to get around not knowing expansion. What expansion is? So the spectral gap. So the mixing lemma tells us that. I guess it would be a more normal term. Tells us that. A graph is an expander if you can control a certain bilinear form for every choice of sign pattern that you put in. For every choice of sign pattern, you have some cancellation. And that's enough for our problem, but it's actually a little bit too strong. Without proving expansion, you can prove something a lot cheaper, which is to get cancellation not for every choice of sign pattern, but for almost every choice of sign pattern. So you can use much cheaper tools such as the classical tilting inequality and probability. And what you can show, roughly speaking, is that if you, instead of putting lambda here, if you put in an arbitrary sign pattern in the sum that you kind of control, you can show that for most choices of sign pattern, you get some cancellation in the sum. So this sum is small for most sign patterns, and the exceptions are very rare and very special. They're exponentially rare, and they're sort of they have low entropy in various senses. Just from the concentration measure, you can get cancellation for most signs. Now, this doesn't help you directly because lambda is not most signs. It could be the sign pattern for which you don't control anything. But what you can do is, in the spirit of sort of these density increment arguments used to prove things like Semrati's theorem and Roch's theorem, you can make a dichotomy. That you have a certain sum, and you want it to be small. And you know also for most lambda, for most sign patterns, this would be small, but it could be that your lambda is a very rare choice of sign pattern for which the sum is large. But in that case, in that special case where you have this sum is large, what you can show is that this implies some information theoretic correlations. More precisely, if you look at a random number n and you look at a random window of the Luba function, you look at this random sign pattern as n slides along numbers from 1 to x. This is some random variable. This is n tuple. It takes values in some Hamming cube. If this sum is large, you can use this Hüfting inequality to imply that this random variable has some entropy constraints. It can't be sort of completely uniformly distributed. It has to actually correlate with, this random variable has to correlate with what n is doing mod p for various primes p. What you can show is that if the sum is large, then this random variable, this n tuple, has some large Shannon mutual information. Has large mutual information with the residue classes of n mod p for various p. That it's a very weak form of periodicity. That it's sort of coupled to a zero entropy sequence. It has sort of low entropy. And you can use that together with Shannon entropy inequalities. And what it tells you is that if the sum is large for some h, then the entropy of this sign pattern, the entropy could be large, but if you increase h So as you make h bigger, this entropy increases. And it could increase linearly at worst. So if you make h k times bigger, this entropy could increase by a factor of k. But because of this mutual information, you can show that if the sum is large, the entropy, normalized entropy, if you divide this entropy by h, the normalized entropy actually has to drop a little bit. That the sequence has some very weak periodicity properties which make the entropy grow slightly sublinearly in h as you increase h. So there's a slight drop in average entropy as you increase h if this sum is large. And so you can keep iterating this. You make h bigger and bigger and bigger. And the entropy keeps dropping. And at some point, the entropy has to stop dropping. And you approach sort of the Kolmogorov-Sinai limiting entropy of your sequence. Whenever it stops, well, actually, it becomes metastable more technically, but then you don't have any mutual information, and then the sum becomes small. Okay? Once you sort of don't have any mutual information, then lambda becomes more like a typical sequence, and then the Hofting inequality lets you control the sequence. So there's this entropy decrement argument, which is very analogous actually to these density increment arguments used to prove the Ross theorem, which lets you avoid the fact that you can't prove expansion, or we don't know how to prove expansion for every scale, but you can always find by the Piccinino principle one scale for which something good happens, and then you can prove this. And this is how we prove this Chowler conjecture, which in turn implies the discrepancy problem. Okay, so I think that is a good place to stop. Thank you very much. Yeah, the quantitative bounds are fairly terrible. I haven't worked on that completely, but I think if you want a sequence of length n, the lower bound of discrepancy, if you unpack everything, is about 5-fold log of n, log, 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 log n. Yeah, there's this entropy decrement argument, it only barely works. Yeah, if you look at my paper, there's I need the fact that sum over 1 over j, log j, log j, log log j, log 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 j diverges. Okay, that's what makes my entropy argument terminate. Yeah, so it only barely works. Yeah. Yeah, by coincidence, yes, actually, by the Gauss bounding. Yeah, okay, that's it. Yeah.
So any stronger smoothing would fail? I mean, there's one over n smoothing, is that critical?
Yeah, I can do something slightly better. I mean, so you can bound n between x and say x over y. Yeah, so I can get a. I can get any bound like this for as long as y goes to infinity, as x goes to infinity. Okay. So it's sort of arbitrarily.
This entropy argument, so that is more than one.
Yes.
The information lambda n plus 1 n x is bounded by a constant less than 1, less than x.
Yes.
So they have to break through getting a constant there.
Right.
Is it true that your smoothing, suppose they did it with 3, with a constant, with your smoothing and allow you to get that constant arbitrarily small? Is that a theorem? Suppose they, suppose you have 3 there,
Right.
without the n,
Right.
but they proved to us in 1 time.
Okay, yeah, so without this n, this whole method doesn't give anything. Yeah, so we
I'm saying suppose that you're able to get your triple sum is less than the constant, like they did, less than x, less than.
Yeah.
So I'm just trying to understand the extent of your entropy.
Oh, okay. Yeah, I can't do.
And you then smooth and then you get that constant to be arbitrarily small.
I don't think so. I don't know of any way to do that. Yeah. We are working on trying to get this. I mean, yeah. So we don't yet. Yeah, we would love to prove that this is log log x. And actually, this is the work in progress, which is, well, okay, nowhere near completion. Yeah.
Any more questions? Okay, so
Yeah, so the best example we know of the discrepancy is log n in the scalar case. In the vector value case, you can make it square root log n by a simple trick. You take the Bowen-Choi-Kunz example, and instead of plus or minus 1, you take plus or minus some element in an orthonormal basis. You can make it slightly better, square root log n. But yeah, and other examples suggest that this is the truth, but the method so far is not going to prove that.